أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Today we'll be talking about field effect transistor. This is actually a type of transistor that is frequently used, and in this particular type of transistor we can control the magnitude of current with the help of potential difference. So this is a specific type of transistors that is a part of the introductory electronics course we will discuss today in the lecture number 16, having and the course code for this particular case is PHY201. And in today's lecture our basic objective is to understand the type of field effect transistors. We also need to know the construction of field effect transistors, and the output characteristic of field effect transistor is also the part of the lectures. So coming towards the type of field effect transistors, the biopolar junction transistors is actually a current control device. The basic objective of this is to control the output characteristic of the device with the help of base current. So in the field effect transistor, the output characteristics are controlled by input voltage, that is the electric field, and not by the input current. So there are basically two types of field effect transistor what we are using. One is the junction field effect transistor, another is the metal oxide field effect transistor. In simple junction field effect transistors, there is a junction field effect transistor in which three terminals of semiconductors is used, and in this particular case the current conduction is by one type of the carriers. I mean electrons are holes. That is why it's also called as a unipolar junction transistor. In comparison to BJT, where that is called as biopolar junction transistor, where two type of carriers are used, both electrons and holes. If you look toward the construction of junction field effect transistor, it consists of p-type and n-type silicon bar containing two p-n junction at the sides. That is shown in the next slide. We will have some channel p-type and n-type channel, so that is the main junction which is represented here. We have a drain for that particular case that is represented by D. There is a gate that is represented by G, and there is a source for that particular case. If you look toward this particular case, this is made of P and this is made of P type of materials, and this hole is made of N type of material. This is a type of N channel junction field effect transistor. If you look toward the P channel junction field effect transistors, then it is like this channel is made of P, and N is N type material is present at this region. So in this way, this is a basic construction of the field effect transistors. So the p-n junction forming diodes is connected internally to a common terminal called the gate, and that is taken out, and the other terminals are the source and drain taken out from the bar that is represented here. So now we are coming towards the schematic symbols of junction field effect transistors. Here is the vertical lines in the symbol. It's maybe thought as a channel in the N type, and the arrow on the gate points toward the channel as shown here. So here similarly for the P type of materials, for the P type of transistor that is called as P channel junction field effect transistor, the arrow on the gate points from channel to gate. JFT, I mean junction field effect transistor polarities. I mean how we can control the polarities of junction field effect transistors. So here in this figure it is shown that N channel junction field effect transistor polarities. In case of this is a type of N channel, and in both cases we have N channel, and this is connected with external circuit. In this is here we have an open circuit, and there is a closed circuit, so the current flows through that, and this is the region where the current is passes, that is the measure, and the P region can control the magnitude of current with the help of that. Okay, and we can control. So this is actually the structure of junction field effect transistor, and the junction field effect transistor polarity is the direction of current that is flowing through that. The Flowing points may be noted as this is the input circuit, that is the gate to source of a junction field effect transistor, that is reverse bias, and this means that the device has high input impedance. The drain is so biased with respect to the source that the drain ID current flow from the source to the drain. So in this particular configuration we have this. So what is the difference between the main difference between the junction field effect transistor and bipolar junction transistor? If we look toward the junction field effect transistor, there is only one type of carriers, that is the holes in the p-type channel and an electron in the n-type channel, but for that is why it's called as a unipolar junction transistor. But if you look toward the BJT, that is the bipolar junction transistor, because both holes and electrons are used in the same transistors. If we come toward the input circuits, that is gate to source of a junction field effect transistor is reverse bias, therefore the device has high input impedance. However, the input circuit of an ordinary transistor is forward bias and hence has low input impedance. So if we look toward the primary functional difference between the JFET and the BJT is that no current, actually a very small current, enters the gate of junction field effect transistor when gate current is equal to 0. However, in typical BJT, base current might have a few micrometer, when junction field effect transistor gate current is 1000 times smaller than that. The other difference between them is that bipolar junction transistor use a current into its base to control a large current between the collector and emitters. But in case of JFET, uses a voltage, that is actually the potential difference, to control the current. In BJT, gain transistor gain is characterized by current gain, where in junction field effect transistor gain is characterized by the transconductance, that is actually the ratio of the change in output current to the input voltage. Similarly, in junction field effect transistor, there are no junctions as an ordinary transistor, but in the conduction is through n-type or p-type semiconductors material. While in case of that is why the junction field effect transistor is very small in structure. Looking toward the structure of this material, we can come across the structure and working of the junction field effect transistors. There are two p-n junctions at the side from the two depletion layers. So the current conduction by charge carrier, that is the free electron in this case, is through the channel between the two depletion layers and out of the drain. The width and hence the resistance of this channel can be controlled by changing the input voltage. So the narrower channel means greater resistance, and hence source to drain current decreases. In reverse, and reverse will happen when VGS decreases. So this is why that if we narrow the regions, the current flow will be slow, and if we open up the region, the current flow will be a bit high. So in other words, the magnitude of drain current can be controlled by altering the VGS. So this is a simple structure. We can control, if this region is narrower, the drain current is low, and if this region is bigger, so the drain current is high enough. So this is actually the structure of junction field effect transistors, where we have this is n channel, and this is actually the direction of current that is flowing through that. So in case of n channel junction field effect transistors, it will be, the direction of current will be like this. Here it is clarified. This is actually open circuit, and this is the closed circuit. So working of junction field effect transistor is clarified here. When the external potential difference is applied between the drain and source would happen, the two p-n junctions at the sides of the bars establish the depletion layers. So the electron will flow from the source to drain through the channel between the depletion layers. So the size of these layers determines the width of the channel and hence the current's conduction through the bar. Whether this depletion layer, the width of this depletion layer increases or decreases, it depends upon this drain voltage. So that actually describe the working, or the it can control the magnitude of current passing through that. So consequently, the current flows from source to drain, that is decreased when the channel is reduced. And in some other extreme case, if the voltage reverse voltage is applied, so what happen, the width of the depletion layers also decreases, and that increase the width of the conducting channel, and hence the source to drain current effect due to that. So we have output characteristic for junction field effect transistor. In that particular case, we have the curves that is drawn here, and the curve between drain current and drain voltage is clarified here. So what happen, we have here the ID, that is the drain current, and this is the potential difference, that is drain to source, that is applied, and this is characteristic for VGS 1, 2 and 3 volts curve for that. So what happen, initially the drain current rises rapidly with drain to source voltage VDS, and then it become constant. So the drain to source voltage above which the drain current become constant, and now this pinch up voltage. This particular voltage is called as pinch up voltage. The pinch up voltage is mentioned here. This is called as VP, and this is called as pinch up voltage. So after pinch up voltage, what happen, the channel width becomes so narrow that the depletion layer almost touch each other. So the drain current passes through this small passage between the layers, and therefore there is an increase in drain current is very small with VDS. So above the pinch of voltage. So what happened, the drain current remain constant at that particular region. If we come toward this particular curve, you see this one is constant, and if we further increase the VDS, there is no change in current. So the because the channel become constant after that region. There is some silent feature of junction field effect transistor. It is actually a 3-dimensional voltage controlled semiconductor device. The basic objective of this device is that input voltage controls the output characteristic of junction field effect transistor. The other thing is that it is always operated with gate to source PN junction reverse bias. So in junction field effect transistor, the gate current is 0. Some other, since there is no gate current, the particular value. So the junction field effect transistor must be operated between VGS and VGS off. So for this range of gate to source voltage, ID will vary from a maximum of IDSS to a maximum of almost 0. And some of the other features is that the two gates are at the same potential. Both depletion layers widens or narrows down by an equal amount. So in other thing is that the junction field effect transistor is not subjected to thermal runaway when the temperature of the device increases. So the drain current is controlled by changing the channel width, and this is some of the features of the junction field effect transistors. Some other analysis, an important term that is relevant to junction field effect transistor is the pinch off voltage, the gate to source cutoff voltage, and the shorted gate drain current, that is peripheral. So we need to explain that important terms in detail. First of all, we need to know the shorted gate drain current, that is called as IDSS. So it is actually the drain current with source short circuit to gate, that is called as VGS is equal to 0, and the drain voltage in this particular case is equal to pinch off voltage. So that is also 0. This is the configuration for that, and this is the particular active region where it is operating. This is the pinch off voltage, and in this particular case the current is IDDS, that is mentioned here. And in this particular case we have the background when break down when we further increase over this region. Some of the important thing regarding the IDDS are the that it could measure under shorted gate condition, and it's a maximum, its value is maximum. It is the maximum drain current that you can get with normal operations. So there is a maximum drain voltage, that is called as VDS, that can be applied to a junction field effect transistor. The region between VP, that is and VDS, that is the breakdown voltage, is called as constant current region or active region. This is the region what I had mentioned here. This is actually called as the active region or constant current region. This region starts from this point P, that is the pinch of voltage, and it ends at this point. So this particular region is called as the active region, that is presented here. So there is a maximum drain voltage that can be applied to junction field effect transistors, and it can control. So this particular region between the VP and VDS, that is actually the breakdown region. Between the VP, that is the pinch of voltage, and the breakdown voltage is called as constant current region, that is I had already mentioned in the figure. So here we need to know the pinch of voltage. The pinch of voltage is the minimum drain source voltage at which the drain current essentially become constant. Here in this figure it is represented, the pinch of voltage is represented. This is actually the drain current, this is the VGS, and this is actually the pinch of voltage, that is over here. So for values of VDS greater than VP, the drain current is almost constant. It is because when VDS is equal to the constant quantity and its magnitude is equal to constant. So what happen, it may be noted that for proper junction of function of field junction field effect, and it's always operated for VDS is greater than VP. So this is the some of the condition for that. The other thing is gate source cutoff voltage, that is represented by VGS. So it is the gate source voltage where the channel is completely cut off and the drain current becomes zero. So this is some description about the junction field effect transistor and its explanation. The most important term what we are using here is the effect, the three terms that is using, and that is the operation condition for that. And this is actually the curves for that explain. This curve actually describes that is described between the drain current and the VDS. So the three terms that is important to us, that is the shorted gate drain current, that is IDDS, and this is the magnitude of that. And the other is the pinch of voltage. The pinch of voltage is on the horizontal axis, the IDDS is on the vertical axis, and the third one is the gate source cutoff voltage, that is called as this one, gate source cutoff voltage. It is called as VGS off. It's VGS off. So this is some behavior of that. So this is important thing, and among all these things the most important thing is the active region, where in which we have a constant current here. If you and physically we can interpret the constant current like that if we increase the magnitude of this potential difference, then this width increases, and there is a constant width that is presented over here. So after this constant width we can see that if we further increase that, there is no change occurring in the current. So in this particular region the width of this channel become constant. When the width become constant, so the current that is passing from source to drain is also become constant. So that is why this is the active region. Here if we look toward the characteristic curves, in all of this the common thing is that at some particular values, at some particular gate source voltage, just like for VGS 3 volt, 2 volt and 1 volt, we see that the common thing is that at some particular values this current will become constant quantity, and this is the physical interpretation of that the constant current is only because of the width of the channel become constant. The most objective of this junction field effect transistor is that we can control the current with the field. The field and the field can increase the width of the channel, increase or decrease the width of the channel, and consequently the current passes through the current passing through the width may increase or decrease depending on the width of that particular region. So this is something about the junction field effect transistor and its explanation. In upcoming lecture we will discuss some more information about the metal oxide semiconductor field effect transistors. Thank you very much for now.